to Introduction to C++. My name is Kate Gregory, and I'm introducing you to the most popular general-purpose programming language, C++. In this module, you'll meet the rather amazing number of operators C++ has for performing arithmetic, comparing, and so on. There are some pitfalls waiting for you, and I'll show you what often trips up beginners to C++. You'll also learn how your own classes can get in on the operator story by writing your own overloads of common operators for your code. Most applications perform calculations of some kind. They add, multiply, and divide numbers. And C++ has the operators you'd expect to do that. Hopefully no one's really surprised to see this list. But one of the interesting things about C++, and this goes back to its C heritage, is that it has operators that other languages may or may not have. And the reason that they are in C++ is because they are a single instruction on some of the chips the language was designed to run on. The plus equals and minus equals operators are actually quicker, in the absence of an optimizer, of course, than the long way. X plus equals 2 and x is equal to x plus 2 are the same in terms of the answer you get, but in a time before optimizers, x plus equals 2 could actually be quicker. These days, the issue isn't about the performance, but it is about readability and about typo prevention. If your variable's not called x, it's called number of units that I need to ship, then being able to write plus equals amount in new order is shorter line of text and less chance to make mistakes than if you have to repeat that really long variable name a couple of times. If you want to add just one or take away just one, there is also the increment operator. And there are two variants of each of the increment and decrement, and they're known as prefix and postfix, depending on whether the symbol comes before or after the variable that you're incrementing or decrementing. The difference between them has to do with what this operator returns. You know, all operators have a return value, so 2 plus 3 returns 5. In C++, even the equals operator has a return value. If I write x equals 2, that expression actually returns the value 2. I++ returns the old value of I and then increments it, whereas ++I increments I and then returns the new value. And the same for the decrement, I minus minus returns the old value of I and then decrements it, minus minus I decrements I and then returns the new smaller value. Why would anybody care about this distinction or even want this operator? I'll show you that when we get to the demo. The percent symbol is the modulo operator. That's your remainder after you divide things. So in this example here, 17 divided by 2 is 8 remainder 1. And the modulo 17 mod 2 is 1, that remainder that's left over after you divide. Quite often you'll see people testing modulos against 0 as a quick way of showing whether or not something is a multiple of the smaller number. The one operator that seems to be missing is the exponent operator, x to the power of y. You can't invent your own. You have to settle for using the POW function, which is in math.h. One of the reasons you can't invent your own has to do with the order of operations. C++ knows the rules that you probably learned in grade school about order of operations. So if somebody writes 3 times 2 plus 1, you're supposed to do 3 times 2 first and then add 1 to the result. I don't recommend learning them. I recommend you use round brackets to gather things up, because even if you learn them all, does the person who's going to read your code know them all? It's often a good idea to express your intent really clearly with brackets. I tell people brackets are free, and they really make sure that everybody understands the order of operations for these calculations that you're doing. I have a project with some simple code in it to demonstrate these operators. Now, I don't have any classes in here. This is just some relatively artificial code, just so that you can see how they all work, and hopefully none of them are any great surprise. I'm going to just run the project and show you the output next to the code that produced it. So we do a number of things to I and just keep printing it out. So we start out with I equal to 0, prints out as 0. Then we use the plus equal operator to add 2 to it, becomes 2. We use the times equal operator to multiply by 3, becomes 6. We use the minus equal operator to take 2 off of it, becomes 4. And we use the divide equal operator to divide it by 4, and it becomes 1. I don't have any demo of plus, minus, times, and divide, but I thought I'd show you these 4 convenience operators. Now let's scroll down a little and take a look at the increment and decrement behavior. You can see I'm using all 4 of them here. I'm going to start by setting j equal to I++. And then I print out I and j. Because I++ returns the old value, which is 1, j is 1, but I has been incremented to 2. When I go plus I, they both come out as 3. So the 2 is incremented to 3, and then that's what we return. J is equal to I minus minus, j stays at 3, and then I is decremented to 2. And finally, j minus minus I, the 2 gets decremented down to 1, and then they both get the value of 1. Those lines of code that we've just gone through, they're really artificial. Why would you write int I equals 2 and then add 3 to it or what have you? It doesn't mean anything. Here's an actual use of the increment operator, kind of semi-realistic. I'm going to run a loop. I'm going to start I equal 2 and go while it's less than 101 and have just a single line in my while, which is that I'm going to call is prime. And I'm going to call is prime with the current value of I, and then I'm going to increment I. So in this single line, I'm able to run around the loop from 2 up to 101. And I've taken this function is prime, which you may remember from other demos. It returns true or false whether the number is prime. And if it returns true, I'm using an immediate if, I'm going to add 1 to j. If it returns false, I'm going to add 0 to j. So I'm counting how many prime numbers there are between 2 and 100. 101 is not strictly less than 101, so we'll stop after we've processed 100. When this runs, it claims there are 25 primes, and you're welcome to count on your fingers and establish whether that's correct or not. The real purpose of the code is to show you an actual use for the increment operator, and for it being important whether I called I++ or ++I. If I were to call this with ++I, the first number that would get passed down to is prime would be 3, not 2, because we'd increment it and then call it. We'd actually get a different result when we ran this. For if, while, and for, we were pretty repetitive in terms of the condition that went in those brackets. Very often we're just comparing that x was greater than something, because I didn't feel like explaining all the different comparison operators. So now let's do that just for the sake of completeness. We have, of course, less than, greater than, less than or equal to, and greater than or equal to. Hopefully those are familiar from other languages. Not equal to in C++ is exclamation mark equal sign, and the exclamation mark in general is a not. I'll show you that shortly. And equal to, super important, 2 equal signs. A single one means that you are assigning a value. 2 when you are comparing. You can combine your comparisons with the and or operators, Boolean and Boolean or, which are always spelled, if you will, with the double characters. So 2 capital 7s or 2 or bars to get a Boolean and or a Boolean or. Now the Boolean and ors are what we call shortcutting operators. So the sample you see here, we say if x and foo at x. If x is false, there is no way for this expression to work out true. False and anything is always going to come out false. And C++, which is all about power and efficiency and everything else, will not evaluate the other half of the expression. It can't be important. No matter what it is, the thing's going to come out to false. And so we say it's a short-cutting operator. Foo will not get called. This may or may not matter from a performance point of view, but if foo has any side effects, this is super important. It's super important that you don't think foo always gets called, but also this is a popular idiom to protect bad things happening. If foo is some function that will blow up when you pass false to it, this will guarantee that it will never be passed false. That may seem silly. Why would you write a function that blows up when you pass false to it? But remember that 0 matches false, everything else matches true. And it's quite likely to write functions that blow up when they're past 0. And this is a way to protect that function from being called. You also have shortcutting like this with the or. If the first one is true, it doesn't matter what the second one is, true or anything will come out true. And again, it won't call the second one. But it's more common to see as an idiom the protection with an and. They both shortcut, however. The not operator, as I mentioned, is the exclamation mark. You can use this just to negate something you already have. So you can say if not x. You can write weird stuff like if not brackets x is less than 3, but it would make more sense to rewrite that using the greater than or equal to operators. But you'll quite often see it for functions that return true or false using not to flip around the return value from that function. I have another very trivial demo just to show what happens and what sometimes people get confused by. So we have this local I, and I'm going to test to see if it's 3 or not. And if it is, I'm going to print out that I is 3. You would expect when I run this that this would not print out that I is 3. Then I'm going to print out the value of I again. You'll see that it's 2. And we're going to test again, but here I'm making a, quote, mistake, unquote, of using a single equal sign rather than a double. If this returns true, I'll print out that I is 3, and then I'll deliberately set it equal to 4, hoping then for a failed comparison. And now here I have a kind of a backwards comparison. People sometimes call this Yoda syntax, and I'm comparing 3 to I instead of I to 3. Either way, it should come out false, so we should expect not to see I is 3. Let's run this. And I'll just put the output next to the code. Let's say we start out and I is not equal to 3, so we don't print this line out. The first thing we print out is that I is 2. The next thing that happens is that suddenly we're told, yep, I is 3. The reason is that this I equals 3 line actually assigns the value 3 to I. Compiler does exactly as it's told, puts the value 3 into I. The equals operation returns 3, the value it just put into I. And since 3 isn't 0, that's converted to Boolean true. The if succeeds and the statement I equals 3 prints out. Here we pump out the value of I again to confirm that sure enough, it is 3. Then we deliberately set it to 4, and testing here, it doesn't print out I equals 3. We printed out the value is still 4. Well, why would anybody write their ifs this way? 3 equals I. The answer is what happens when you make this mistake. Here, when I make this mistake, I still get valid C++ code. This is actually something that happens quite often in real code on purpose. But here, if I take away one of the equal signs, you can't set the number 3 to a new value, so you get a compiler error. And people who are fans of the Yoda syntax are trying to prevent themselves from this error by using their syntax in this order, so that if they ever just forget and type a single equal sign, that they'll get helped by the compiler. Let me just show you, I said this is something people would actually really do, have a single equal sign and an if. I'm going to type some kind of gibberish code. I'm going to call some non-existent functions and prove to you how people might do this. So something you might do, you might declare another integer, call some function, passing in a string, and then if that p is not 0, do something, call some other function. Let's just make this true-ish, at least keep the compiler happy, by just declaring some functions. I'm going to have an integer foo that takes a string s, and in order for that to work, I have to include string. And another integer function called something that doesn't take any parameters. I'm not going to implement these, but simply by declaring them this way, I take away any red wigglies and make it clear to everybody that the compiler is okay with this code. Now let's make it a little nicer. Let's put the braces here no matter what, so that if we add more into what we're going to do when p is not 0, that we won't get messed up by thinking the compiler might read our indents. This is working code. The compiler will compile it, it'll run, assuming I were to have the functions foo and something written, but it's not kind of C++-ish. The first thing is to take this away. It's very non-C++ish to write if whatever equals true, or if whatever is not 0, because they're the same as just if whatever. So when I say if p, that will come out as false if p is 0, otherwise it'll come out true. So if p and if p are not equal to 0, exactly the same. So this is the more C++ way to do it. And the really more C++ way to do it is to take this assignment and put it here. Now I'm in the one breath assigning p to the result of the function call and checking the result of the function call. If it's non-zero, we'll do something. If it's 0, we won't. And this is a C++ idiom that happens all of the time. And for the compiler to warn you when you did this and say, oh, are you sure? Did you really mean to type only one equal sign? Would mess this idiom up. So as a result, there is no warnings. You see there's no red wigglies. And if I were to build this, I would only get linker errors because I haven't actually implemented those functions, but I wouldn't get any compiler errors at all. And I'm going to take this code and just comment it out. And then uncomment some other code that I want you to see. This code is going to ask for a number and figure out if it's prime or not. So we're going to use the isPrime function that's been kicking around in a lot of different demos and the not operator. So isPrime will return true when it's prime. Not will turn that into false. It'll return false when it isn't prime, and notting that will turn that into true, which in this case will cause it to print out not. So it'll write out either 4 is not prime or 5 is prime, depending on the number that I enter. So that's showing you combining the results of a function with the not operator right inside the if. And then I'm going to ask for a second number, j, and I'm going to calculate I mod j, that is the modulus, the remainder, after dividing I by j. So if I is 5 and j is 2, 5 divided by 2 has a remainder of 1. If the remainder is exactly 0, then they're multiples. Right? So if I take 4 divided by 2 that has a remainder of 0, that's because 4 is a multiple of 2. And I've written this out the long way, saying if it's not 0, then it's not a multiple. But again, the more C++ way to do it would simply be to test I mod j. If I mod j is 0, that's false, and we won't go into the if. If I mod j is non-zero, that's true, and we will go into the if and print out the not. So I'm going to run this code and try it with a couple different numbers. So let's try 5 and 2. 5 is not a multiple of 2. Hopefully not a surprise to anybody. Run it again. This time I'll do 4 and 2. 4 is a multiple of 2. Let me show you one other possibility. I'll try 5 again. This time I'm going to ask if it's a multiple of 0. You see what happens? We sort of sit here, and then Windows says, your program has a major problem. And the major problem is that it's thrown a divide by 0 exception, which I could figure out if I were to click Problem Details and scroll through and take a look at the problem. But there's no way to solve it, and I'm not going to submit details. We divided by 0 because I entered 0 for the second number, which is j. There are a variety of ways to cope with that. I could have put in a while loop that said, while the person didn't enter 0, and if I do enter 0, I could put an error message, ask me again, and so on. And honestly, taking the modulus like this may not be the world's most common behavior, but there are plenty of functions out there that expect to get a number that is not 0. And passing 0 will make the function blow up. So we can simulate that with this I mod j calculation. And if I simply say here, if j and I mod j, what's going to happen is when j is 0, that's false, we shortcut, we won't calculate I mod j, we won't throw the arithmetic exception. Now we also won't print out the word not, so I have none of the expression here, but I'm okay with everything being a multiple of 0. So let's run this now and say 0 and watch it not blow up. So I'll say 5 for the first one again, 0 for the second one, and it reports that 5 is a multiple of 0. You may not like that mathematically, but what's important here is the application did not blow up. And the reason it didn't blow up is that this line, which tried to divide by the second number, this expression was never evaluated. And it was never evaluated because the AND is a shortcut. A natural response, the first time you see those Boolean AND and OR operators that are doubled up, 2 ampersands, 2 OR bars, is to ask, why? Why do you need 2 of them? And a natural mistake is to only use 1. When you only use 1, you're using a bitwise operator, not a Boolean operator. I've mentioned a couple times, when you try to put an integer into an if, it gets converted to true or false. 0 is false, everything else is true. So if I want to do 4 and 1, imagine longer expressions, one of which evaluates to 4 and one of which evaluates to 1. That's true, and that's true. Bitwise operators take the individual numbers, line them up as binary numbers, a series of 0s and 1s, and then AND or in the case of the NOT operator, negate, flip the bit, bit by bit. So 4 in binary is 100. 1 in binary is 001. 100 bitwise ANDed with 001. We take the first pair, the topmost bit in each number, 1 and 0, 0. Move down to the middle one, 0 and 0 is 0. And the last one, 0 and 1, still 0. So we get a result of 000, which is false. So 4 and 1 is using a Boolean operator, comes out true. 4 and 1 using the bitwise operator comes out 0, which is false. Completely opposite result. Why would you want it? It's very common to save space and time by packing individual bit values into a single number. If you have some operation which has got 7 different options that you could set, you can take 7 parameters, each of which is just true or false, or you can take a single integer and look at the lowest 7 bits of that integer and see if they're on or off to see whether you want the option on or off. So then, in other words, when someone passes in 4, they're saying that they want the particular option that corresponds to that bit position on and all the other options off. If they pass in 7, that means their number ends 111 in binary. They want those last 3 options on. Nobody works that out in their head and says, ooh, I think I'll pass in 13. Instead, they use bitwise and or to combine typically constants that match to those values. So there'll be a constant defined whose value is 4. There'll be another constant defined whose value is 1. Another constant defined whose value is 8. And when you OR them together, you turn on the individual bits in the flag. When you want to test, you bitwise and to look and see if those bits are on in that flag. Is this a beginner technique? No, it is not. When you're calling those kinds of functions, someone will give you sample code showing that you set the options by passing in the last parameter A, B, C, OR bar, only one of them, D, E, F, OR bar, GHI, where those letters represent individual constants. For example, if you're writing a message box call, there's an MB underscore OK and an MB underscore cancel. And if you OR them together, you want both an OK and a cancel button. And the fact that it's bit packed under the covers can be completely hidden from you. If you know the trick, you'll see the single OR bar and go, oh, I get it. We're setting bits in an integer. But you don't really need to know. I consider it to be a non-beginner technique. It's really only something I need to mention to keep you from accidentally using it. You're always going to use the double ampersand Boolean and the double OR bar OR for your typical Boolean calculations. In the interest of completeness, I'll also mention the bit shift operators. You've met these in their guise for putting input and output, but they actually existed first in the language as a bit shift technique, where you write the number out in binary and then move all the bits over one direction or the other. Moving all of the bits leftwards is like multiplying the number by 2, because everybody moves up a power of 2. And moving all the bits rightwards is like dividing by a power of 2 and throwing away the remainder, because all of the bits move down. Again, not a beginner technique, but if you happen to see people putting these operators with numbers on both sides of them, it's not about writing to the screen or reading from the keyboard. It's about shifting bits around in a packed bit flag. It's almost never what you want to do if you're just getting started in C++. I'm not going to show you a bitwise demo. If you want to play around with these, you're welcome to fire up a console app and put some of these in and see that the examples here on the screen are true, and make some more up of your own if you're interested. Bit twiddling can have tremendous benefit. It can also be tremendous difficulty, and there's some very fiddly, worrisome bits that I don't want to get into, because in general it's not a beginner technique, not something you need to know in order to do effective work in C++ starting from day one.